All right, so now we're going to do a little video on Riemann sums. This is still target B5, so 0B-5, where we're just doing applications of integration. Now, Riemann sums actually came before area. So remember, this is the example of a Riemann sum written as a limit. It's the limit, and if you remember when we did area, let me just sketch something out here, going from A to B. So let's say I've got a function here like that, and I want to find the area under this function from A to B. So we want to find this area. So what we did when we first started learning about area was we used geometry shapes. We broke it up into triangles and rectangles and trapezoids and semicircles and things like that. And then we started talking about Riemann sums, which Riemann sums focuses on rectangles. And you can do rectangles that are left-sided rectangles, right-sided rectangles, midpoint rectangles, right? We did those. All right, and then we started thinking about, okay, if we actually want the accurate area underneath this graph from A to B, then we want to sum up all of these rectangles, and then we also want to make as many rectangles as we can. So this expression of this limit is the summation of a bunch of areas of rectangles. This is f of x, all right? And notice we have f of this quantity times this. Well, this is the height of the rectangle, and this is the width. So if you take b minus a, that would be how long this is. And if you would divide by n being the number of rectangles we're using, that would give me the width of each rectangle. So b minus a is this length, and divide that length into n number of rectangles, that gives me the width of each rectangle. All right. Then this f, I wish that was bigger, f of this expression tells me the height of each one of these rectangles as we go along from A to B. So you start at A, and then you do a counter. All right. Your counter is like your first rectangle, your second rectangle, your third rectangle. All right. So A is where we start. And then if we do the first rectangle is going to be A plus, we're adding one width here. So notice B minus A over N is the width of the rectangles. So we start at A and we add one width, because I'm going to put K as 1. And so that's giving me the right-sided, this ends up being a right Riemann sum is what this is, a right-sided rectangle Riemann sum. So then when you put a 2 in here, you're going to add 2 of these, so 1, 2. So that would give me the height of this second rectangle. And then when you plug a 3 in here, it's A plus 3 of these widths, so that would give me the height of the third rectangle. And what you're doing is you're summing them up. That's what a sigma symbol does, sums them up. And then we're going to sum up 1 to n. So we can do 10 rectangles, we can do 100 rectangles. Then we're going to make the limit and let the number of rectangles go to infinity. So we're going to do an infinite number of rectangles. And when we did this last year, these two things, the limit and the sigma symbol, they become the integral sign. So this leads to the integral from A to B of f of x. This is f of x. This is x. Here's f. And this becomes the dx, because when you put an infinite number of rectangles in here, the width of each one of these is infinitesimal. It gets really, really small. So that becomes your dx. So this is the integral from A to B. This is the height times the width of each rectangle. All right. So that's where the integral came from. I hope you remember talking about that. So what I want to do is I've given you a circuit involving Riemann sums, and your idea is you want to go back and forth between the limit expression and the integral expression and be able to convert back and forth. And this is not hard at all. All you got to do is be able to find A and B and what your function is, and you're good to go. All right, so the limit and the sigma symbol, the epsilon symbol thingy, summation, those are in the limit expression all the time. So it's the limit as n goes to infinity of the summation of k from 1 to n, blah, blah, blah. All right, so in here, remember, this is your function of something plugged in. All right, so this is my function here in this first one. So I can already tell my function is the square root of something squared, so x squared plus 3. I can already tell that that's the function looking at this, because inside this first set of parentheses matches with this part right here. So it's a function, and this expression has been plugged in. All right, so here's the k, matches the k right there. So this b minus a over n, 4 is actually the b minus a. So I know right now b minus a is 4. So the difference between, on my integral sign, the difference between my a and b is 4. And inside this expression, the number that's added inside the function, here's the function. All right, here's what's been plugged in for my x, is something plus 1. So here is my a value right there. So b minus a over nk plus a number. So here is b minus a over nk plus a number. So here's a right there. So that means my integral starts at 1. I can tell by looking at these two expressions here, the b minus a over n's. This is your b minus a over n, and this is your b minus a over n. So we know b minus a is 4. So if we start at 1 and the difference is 4, then b is going to be 5, because b minus a has to equal 4. So that has to be 5. And there's my answer. I'm done. That's it. So this is the integral from 1 to 5 of the square root of x squared plus 3. All right, it is that simple. Okay. All right, next one. And if you want to pause it and try it first, do it yourself first, and then check the answer with me, you can. Pause it now and then start me up later. All right. So I want to do the same thing. Find the integral from this one. We know the limit and the summation symbol, they're always there. So here, right here is my f of x, is my function. So it's the integral of this thing. So this is x cubed minus x. All right. And notice this expression in here, the b minus a over n, that's the 7 over n. So I know b minus a has to be 7. Notice this doesn't have anything added to it. There's nothing plus something, right? This is 7 over nk. There's no plus anything with it. 7 over nk, there's no plus something. So that means a has to be 0, because there's nothing added on to these guys. So that means my integration starts with 0. I know b minus a is 7, so that means we're going from 0 to 7. This is x cubed minus x, because this function, this expression has to be plugged into a function. So it's this quantity to the third power minus that quantity. So those were plugged in for x. So that's x cubed minus x. And then this is your b minus a over n again. So there's my answer. Boom, done. Easy peasy, right? All right, so now let's reverse it. Okay, now let's write the limit expression. So let's do the limit expression. So now I've got the integral from 2 to 6. I got a square root of x dx. So now I want to write this. So I know it's going to be the limit as n goes to infinity of the summation k from 1 to n. All that stays the same. All right. So now what I got to do is I have to put in here, I have to put the function. All right. So here's my function, square root of x. So what am I doing to square root of x? I am plugging into that my a is the bottom subscript, so that'll be 2 plus, and then I want b minus a over n. So b minus a is going to be 4, so that's 4 over n. Put a k beside it. All right, so there's the first part, and then that gets multiplied by b minus a over n, which is the same thing, 4 over n, and I'm done. It is that simple. That's all there is to it. You just got to make sure you figure out who a and b are, and what the function itself is, which they give you the function. So you're just substituting into that function a, which is your bottom. This is from a to b. A is your lower subscript or lower limit of integration. So that's your 2 plus, and then b minus a is 4. So 2 plus 4 over nk is what gets put in here in place of x. 2 plus 4 over nk gets replaced with x is. And then multiplied by another 4 over n. That's my answer. Boom, done. All right, so if you want to try this one on your own, you can pause me and then unpause me here in a second and check yourself out and see how you do. All right, so the answer is going to be the limit as n goes to infinity of the summation of k from 1 to n. So now I need my f of x, which is sine squared of something. Sine squared of some expression. Now, what am I putting in place of x? I'm putting all this. All right. So I need my a number. My a number is pi over 2. Plus, now I need b minus a over n. So b minus a, well, 3 pi over 2 minus a pi over 2 is just going to be pi. So that's going to be pi over n times k. So pi over n times k. And that gets multiplied by pi over n. No k, just the pi over n. And that's your answer. That is it. Boom, done. Bada bing. All right. So you just have to recognize who A and B are and just put them in there. Just subtract B minus A for the B minus A's. A is the lower subscript. That's added on. Just notice the K is in where the X goes. Wherever they don't put a K back here, it's only B minus A over N. All right, that's it there. So now here's one where you have a picture. So I want the limit expression that goes along with this picture, and it's the shaded area under x cubed. So this right here is the function, part of the function x cubed from 1 to 4. So the first thing I always do if I'm given a picture is I'll write the integral first. So this is my integral from 1 to 4 under x cubed dx. So that's what I'm doing. So now I want the limit expression that goes with that. So the limit as n goes to infinity, the summation of k 1 to n. I need my function. So my function is x cubed. So I've got something cubed, and what goes in here? Well, this goes in here. So I need the a value. So my a value is 1 plus, and then I need b minus a. So b minus a is going to be 3 over nk. And so then you multiply that by the b minus a over n. So that'll be 3 over n. And there's your answer. That's it. That's all there is to it, going back and forth between Riemann sums and the integral. And just remember, all this is summing up an infinite number of rectangles, all right? And you're finding the area under the curve by making the number of rectangles go to infinity, and that gives you the integral sign. So that's just converting back and forth between those. So I wanted to give you a little refresher on that. Just that came all before area, before we started doing the integrals. I just wanted to give you an idea, remind you in case there's a question like that on the AP exam.